Buckle up, everybody, because today we're going down a rabbit hole. We're talking many worlds interpretation. That's right, the theory that says every quantum measurement spawns, well, like a whole new reality. Yeah, it's a lot to wrap your head around. And as if that wasn't wild enough, we're going even deeper.
We're tackling a question that has bugged physicists for ages. If every single possibility plays out in some reality, in some world, well then what does probability even mean?
Right, exactly. I mean, if there's a me out there experiencing every possible timeline, how can we say one outcome is more likely than another? It's like, are we all just living in some cosmic lottery? And to help us unpack all of this, we're diving into a paper, get ready for this title, Self-Locating Uncertainty and the Origin of Probability in Everettian Quantum Mechanics.
Quite a mouthful, isn't it?
It is. It's dense, it's complex, but it digs into these really fundamental questions about, like, the very fabric of reality, you know?
And that's why we're here, to break it down, make it clear, have some fun with it.
Exactly. So before we go too far, let's recap this many worlds idea.
At its core, it says every time there's a quantum measurement, the universe doesn't just pick one outcome. Instead, it branches off, creating new timelines where each possibility actually happens.
Okay, so, like, it's not just a coin flip landing on heads or tails.
Right, it's both.
That's
In
its
one
term.
world, it's heads, in other, it's tails. And the kicker is, both of these worlds are real.
Okay, I'm with you so far. But, and here's where I get tripped up. How do we, as observers stuck in this multiverse, how do we make sense of probability? Like, if everything actually does happen, shouldn't every possibility have the same chance of happening?
Right, it's a very natural question to ask. And it leads to some pretty wild conclusions. One way to think about it might be to just, count the branches. More branches with a certain outcome, you might think, well, that means it's more likely.
Yeah, that makes sense, right? More branches, higher probability.
Seems straightforward, but let's see where that logic takes us. The paper uses this example, the once or twice Alice example, to show why this branch counting idea, well, it kind of breaks down. So, picture Alice. She's measuring the spin of a particle. And let's say there's another measurement set up that only happens if Alice gets a specific result on that first measurement.
Okay, so we're already branching timelines here, creating multiple Alices.
Exactly. Now, if we were just counting branches to figure out the probabilities, then the odds of Alice getting a specific result on that first measurement, those odds would change based on what happens in those other branches, even if those later events have nothing to do with her directly.
Wait, hold on. So just because something happens in another branch, a branch that doesn't even involve Alice, her certainty about her own measurement, what she's seeing right in front of her, that changes. That
Yeah.
feels off.
Yeah.
It's like what happens over there shouldn't mess with what's happening here.
Exactly. You hit the nail on the head. That's the crux of the problem with this whole branch counting thing. It leads to these inconsistencies. Like it suggests that something happening in one corner of the multiverse can instantly change the odds in another, even if there's absolutely no connection between them, no way for information to travel between those branches.
Okay, yeah, that makes sense when you put it that way. But then how do we even begin to make sense of this? The paper, it's got to offer some kind of solution, right?
It does. And a pretty elegant one, if I may say so myself. It introduces this principle they call the Epistemic Separability Principle, or ESP for short. Catchy, right?
ESP, I like it, has a ring to it.
Yeah. So ESP basically says that whatever happens in the environment shouldn't change your belief about which copy of yourself you are, within a set of identical yous.
Okay, bear with me here because I think I'm following, but this is where it gets really out there. So we're saying there are countless versions of me spread across all these different branches, different universes even.
Countless, infinite, pick your favorite mind-bogglingly large number.
Okay, infinite versions of me. And ESP is saying that I shouldn't let what those other me's are doing, what's happening in their realities, affect my understanding of my own reality.
You got it. It's all about focusing on your local branch, your own experience. The paper gives this great example to illustrate this, the duplicating Dr. Evil thought experiment.
Okay, I think I've heard of this one.
So imagine there's a machine that can create a perfect copy of Dr. Evil, right? Down to the last atom, a perfect duplicate.
I'm picturing it.
Now here's the question. What are the chances that Dr. Evil, when he wakes up, is the original?
Well, if the duplication process is truly random, I'd say his odds are 50-50, right?
Right. 50% chance he's the original, 50% chance he's the copy. Now, let's say we build another duplication chamber, but this one's on Mars, and we make another Dr. Evil clone. Does that change his odds of being the original?
I mean, if he doesn't know about the Mars clone, I'd say no, right? His experience, everything around him, it's all the same. It's like you said, what happens elsewhere shouldn't affect his judgment about his own situation.
Exactly. And the same logic, it applies to the quantum realm too.
Hmm.
ESPQM, that's the specific version of this principle tailored for quantum mechanics. It says that when we're thinking about probabilities in this crazy many worlds picture, we should only focus on our local branch, the events that directly impact us, not on stuff happening in other branches that we have no causal connection to.
Wow, this ESP principle, it's so simple, yet so profound. It's like a key to unlocking this whole probability paradox in the multiverse. But how does this connect back to the Born rule, the equation that tells us the probability of different quantum outcomes?
You see, that's the really exciting part. This is where the paper gets really juicy because it shows that the Born rule, it naturally emerges when you apply this ESP principle to the many worlds interpretation.
Okay, now you're speaking my language. Break it down for me.
It's a bit technical, I won't lie. But in a nutshell, the paper shows that the only consistent way to assign probabilities in a multiverse, without running into those contradictions we talked about before, is to use the squared amplitudes of the wave function, which, lo and behold, is exactly what the Born rule tells us to do.
So it's not just some random mathematical coincidence.
Not at all.
The Born rule, it's actually reflecting this deeper truth about how we experience reality in a multiverse.
Exactly. This paper shows that the Born rule isn't just some equation physicists came up with out of thin air. It's a direct consequence of applying a really intuitive principle, this ESP, to this incredibly strange, mind-boggling reality that is the many worlds interpretation.
That's mind-blowing,
Yeah.
really. But I gotta be honest, thinking about probability in a multiverse where everything happens, it still makes my head spin a bit. Are there any scenarios where even this framework, this ESP thing, leads to weird, counterintuitive conclusions?
Oh, you bet there are.
No.
It wouldn't be the many worlds interpretation without some serious head scratchers. The paper actually looks at a few scenarios where this whole framework leads to some really strange, really weird conclusions. One that really caught my eye, I gotta say, was the quantum sleeping beauty problem. Ah, yes. A classic thought experiment really highlights those subtle points about probability when you're dealing with a branching multiverse.
So, walk me through it. What makes Sleeping Beauty's quantum nap so special?
Okay, so imagine Sleeping Beauty, right? She's a bit of an adventurer. She volunteers for this experiment.
Okay.
And they give her a special sleeping potion. This potion makes her completely forget waking up if she's woken up multiple times within, say, a certain period.
Sounds awfully familiar, like my kind of Saturday night. Just kidding.
So while she's out cold, the researchers, they're busy. They perform a quantum measurement on a particle.
Okay, here we go.
Here's where it gets interesting.
Hmm.
If the particle's spin is up, they wake her up on Monday. Then they give her another dose of that memory wiping potion and wake her up again on Tuesday.
Okay, I see where the confusion might set in.
Right. But if the spin is down, they only wake her up that one time on Monday.
Okay, so she wakes up, right, knowing that the experiment happened, but she doesn't remember any previous awakenings. She's got no clue if it's Monday, if it's Tuesday, or if the particle was spin up or spin down.
Exactly. She's in the dark. And here's the million-dollar question.
Mhm.
When she wakes up, what probability should she assign to that particle's spin having been measured as up?
All right, let me think. If we go back to the Born rule, there's a 50-50 chance of the particle being spin up or spin down.
Right. Seems straightforward enough.
Hmm.
But here's where things get a little slippery. On the surface, it looks like a simple coin flip. But remember, she's woken up twice in that spin-up branch. So technically, there are more Sleeping Beauty Mondays in that spin-up scenario.
Ah, so intuitively, you'd think she's more likely to find herself awake in a branch where she gets woken up multiple times, right?
Exactly. And that's where our friend ESP comes in to refine our intuition a bit. Taking into account both the probabilities of the initial quantum measurement and the fact that there are different numbers of observer moments, those awakenings, within each branch. ESTQM, it suggests a 2/3 chance that the spin measurement was actually up.
Wow, a 2/3 chance just from waking up. That's wild. It's like the simple act of observing, of being an observer in this branching multiverse. It adds a whole other layer to this whole probability thing.
It does. And this isn't just theoretical mumbo-jumbo. There's a growing body of research looking at how these principles might apply to cosmology. Maybe even offer some new insights into the biggest question of all. Why is our universe the way it is?
Okay, whoa. Now that's a question for another deep dive for sure. But this whole discussion, I'll be honest, it's really stretched my brain today. So for our listeners out there who might be feeling like their brains just went through a quantum blender, What's the key takeaway here?
I'd say the most profound takeaway, the one that really sticks with me, is that in a universe where quantum mechanics reigns supreme, probability isn't just about the chances of things happening, but about the chances of us finding ourselves experiencing those things. It's a shift from this objective view of chance to a more subjective one. It's about us as much as it is about the universe.
It makes you wonder, right? If every choice we make, every quantum event, every decision creates a new branch of reality, what does that mean for us, for our sense of self? Are we just one version of ourselves amongst countless others?
It's a question that'll likely keep philosophers and physicists busy for centuries to come.
And it's one we'll be sure to revisit. But for now, we're going to have to leave it there. This has been a mind-bending exploration into the many worlds interpretation and the very nature of probability itself. From all of us here at the Deep Dive, thanks for listening.